Hey, Chris, are you there?
Yes, I am. How you doing?
I'm doing pretty good today. How about yourself, sir?
Doing good.
Good, good, good. How's the studying coming along?
Doing pretty good. Doing pretty good. I've already got a bunch of questions on here from my review sheet that I would love to go over.
Sounds good. Looks like you have some stuff here on eigenvalues.
Eigenvalues, and then there should be a couple of things I think on dealing with like diagonalization. And yeah, so a couple things on diagonalization, and really some of the especially like the first two questions. It's the first one specifically. It's I get my answer, but then the answer they're giving me, it's like I'm confused on how they're getting it. It's very similar. Like the numbers are the same, but they have a they're showing a different eigenvector than the one I am getting. And so I'm just trying to correlate the discrepancies there. So, yeah.
Okay, so you're looking at number one here. It says find the
Number one,
eigenvalue and basis.
yep, eigenvalue and basis. Yeah. So, yeah, for 1A there. And give me
Well,
one quick second here. I'm
sure
having
thing.
to run my bit paper off of my tablet right now because I moved my pen for my little writing tablet for my computer,
Hmm.
and I don't remember where I put it. So I'm having to uh, actually use type this into my actual tablet and go that way. So
Well, glad you got a backup plan there.
yeah, I just realized I wish I had realized that like 5 minutes ago, so that oh, that might help if I spell bit paper correctly.
Do you have the link still?
I'm just typing it directly from the URL here, which,
Okay.
with the exception of trying to transpose an T with an R, it was working. Everything was fine. There we go. I am up and running now. So now I got on my big screen and I got on my small screen. So, but hey, all
Sounds
should work
good.
fine. Yeah.
All right, Chris, tell me what an eigenspace is.
Well, eigenspace isn't that going to be a collection of all the eigenvectors for a matrix?
It does. It contains all the eigenvectors as well as the zero vector. Remember, the zero vector cannot be an eigenvector
Right.
due to
Okay.
definition. So it's really all the vectors which will satisfy this equation without the stipulation that x can't be zero. If
Okay.
x is zero, then you are talking about eigenvectors.
Gotcha.
So when you went about calculating the eigenvalues for part A, what did you get for your spectrum?
So for my eigenvalues, I've got my values. And let me just verify. Yeah. So my eigenvalues I got as 1 and -1.
Good. And what did you get for your corresponding eigenvectors?
For my eigenvectors, so for a value of 1, my vector was 1, 1. And for -1, we'll do this. There we go. So for what I got for -1, when I computed it, did it a couple of times. I got -1, 1. But when I compare that with what they're giving me 1, -1. And I'm trying to figure out why that negative is being transposed.
Okay, well, it doesn't really matter here in this particular case because any scaling of an eigenvector is still an eigenvector. So if I was going to take an eigenvector and let's say multiply it by c,
Mm-hmm.
and if you operate, you can pull out the c, then you'll have ax, and ax corresponds to your lambda x.
Okay.
So you can scale it however you want, in other words. So the scaling of an eigenvector by a non-zero value is still going to be an eigenvector. So all they did is say, well, we're just going to use the 1, -1, because if you scale this by -1, you're back to over here.
Okay.
So you can definitely use this. And if you want to write up something like the eigenspace, you might say, depends on how they want you to write in your textbook and your course there, but maybe the eigenspace corresponds to lambda equals 1. You would say the span, and then just pick your eigenvector associated with lambda equals 1, and that's your space.
Okay. Okay, so really it honestly doesn't matter because of scaling factors.
That's right.
Okay. All right. Okay, so no issues there.
Okay.
And then I do want to look at number or B really quickly on this one.
Okay.
So we had 0, 1, -1, 0. Because that one is dealing with we're having to do the quadratic formula.
And what was your spectrum here?
So for this one, you see this. So this one I was trying to figure out. I think.
Make it complex.
Yeah, it's because I was having trouble because I was trying to figure it out with their quadratic formula, but I was having trouble figuring out or figuring out how they were able to do it. Because yeah.
So your trace is going to be 0, and your determinant is going to be 1. So here's your characteristic polynomial, which is the sum of squares. And in order to solve this, you're going to have a really hard time factoring it. Now, you can take the 1, move it to the other side.
Right. Okay.
And then you can take the square root, but that's going to lead you to plus or minus I. So you have complex eigenvalues, and that's completely fine. I mean, that's possible. And sometimes you will. Looks like up here I have something called a skew Hermitian or skew symmetric matrix. And those matrices are interesting in their own right. But anyways, if you want to find the eigenvectors, you would go about the exact same process. You're just going to have some complex entries within your vector. And that's okay. Because you cannot get a real matrix, real entries, multiplied by a real vector, and hope to get a complex. Can't happen. X must contain complex entries, otherwise you're not going to get a complex eigenvalue.
Okay.
Other than that, you work it the exact same way. You just start using complex arithmetic. Take off I off the diagonal. So when we take I off the diagonal, we're going to have negative I, 1, -1, and actually negative I down below. Now, you can take the first row and you can multiply it by I. And you have to remember that I squared corresponds to -1.
Okay.
So what we're going to have here is negative of I squared, we'll have I, 1, and then I. Now, everywhere you see an I squared, replace it with the -1. And negative times a -1 gets you a positive 1. Now add the first row down to the second, thereby giving you 1 I and a row full of zeros. Extrapolate and interpret what you just did. So your vector is going to correspond then to negative I, 1, since the free rule is going to be x2. And that right there is an acceptable eigenvector. You can also pull out the negative if you want. And you'll have I and then -1. Or if you really wanted to, you can also pull out the I. If you pulled out the I, then you're left with a 1 and then -1 over I. And if you had I in your denominator, it's typically we don't want it in your denominator. We want to write it in the standard form of A plus BI. So I would have to rationalize the denominator. And if I want to rationalize the denominator, then I multiply it by I. It's the same protocols you'd use if it was a square root and you're rationalizing. And here's an I squared, so I replace it with a -1, and I'll go about the same business and have I on down below. So there's lots of different ways of how I can express the vector, or I can just go ahead and just take it the way that I have it to begin with. Now, the other vector that corresponds to this system is you're going to get x equals, and you'll have I, and then 1, which does make a lot of sense because complex roots arrive in conjugate pairs.
Mm-hmm.
So if I is a root, the conjugate of it is going to be -I. Or you might recall, in more in general, if you have A plus BI, then it's going to be A minus BI. So if I looked at a matrix with real entries, and it's important that it does have real entries, if I take the complex conjugate, this right here, of the left side and the right side, the complex conjugate of real entries is real. Here, you get your other eigenvalue, and you get your vector. So the corresponding vector corresponding to the other eigenvalue, so if this is lambda and this is lambda conjugate, it's just the complex conjugate of the other one.
Okay.
And that fact right there can help speed up calculations a bit when you have complex eigenvalues.
Gotcha. Okay.
Okay, good. Okay, anything else on number 1?
Nope. That kind of covers everything for number 1 then. Okay.
Good. Okay, let's pull down here. You had a question here about number 3?
Yes.
Okay, what question you have here, number 3?
So it's part C on that one. So finding the eigenvalue with a squared plus alpha a plus beta I, where I is a 2x2 identity matrix and alpha and beta are scalars.
Okay. So what did you try when you worked this problem?
So this one was 3. There we go. So let's see, because this is, yeah, so we have our 2x2 matrix, which is 2, 1, 0, 0, and 3. Oh, I'm looking at the wrong one. Okay. So I wasn't making a lot of sense to me because so we have an identity matrix and we have the scalars. Will they show us then trying to go to the wrong spot?
Well, here's your matrix. If you were to go ahead and just go through the calculations, you would get your a squared plus your alpha a plus your beta I. This is your matrix. And if you did want to figure out the corresponding eigenvalues, you could use this matrix and calculate the trace, the sum of the diagonal entries. So you would have your t squared minus, looks like you would have 13, 5 alpha, 2 beta, and then you would have your determinant. And luckily, it's a triangular matrix. So it's going to be the product of this entry with that entry.
Okay,
Segmental
so
error
the
one.
alpha is going to be the diagonal entry, and then we're taking the square root of that for our this value.
Why would you take the square root of it?
Well, so we're taking the square root of the diagonal because 2 squared, because we have this t squared. So I mean that would make sense.
Well,
But
you
3 squared is
would
9, 2 squared is 4.
you wouldn't do that. What you can use is the quadratic formula. You can set your equation equal to 0. And the quadratic formula, you would have your linear component, and then you'd have your scaling. So let's just say A is 1. This is B.
Mm-hmm.
And this right here is going to be C.
Okay. Well, I'm just trying to figure out how you determined the components for the matrix. So our
Okay.
9 plus 3 alpha plus bravo or beta, and then the 4 plus 2 alpha plus
I see.
beta.
That's going to be t squared minus the trace of the matrix
Right.
times t plus the determinant. And
So,
since it's
but
triangular,
yeah.
product of the diagonals.
Oh, okay. But again, I'm trying to figure out. So the actual variables. So we have 9 plus 3 alpha plus beta.
Mhm.
How did you get the 9 plus 3 alpha? Because 3 is the original component of the matrix from up here.
Mhm.
Now the 9 again, is that just the square root of the original entry, or
I'm
not square root, but
squaring.
the square?
I'm following the
Okay,
formula right here. And I'm using this matrix right here
okay,
to get the matrix down here.
gotcha. Okay, perfect. Okay, now I
Good.
see. Okay,
Good. Now, if I actually want to figure out what the eigenvalues were, I could grind through this whole entire process and just keep going. Like that.
mm-hmm. Ooh, that is that's going to be a
Okay.
hefty thing there. So
I could do this.
could.
But Chris, I don't want to do that.
No, we don't.
That's hard. And what we want to do is think like a scientist. What can I do to make this a little bit easier? So let me pull the problem over here and take another look at it. Okay, so when you're first doing this, what did you actually get for your eigenvalues for A?
Eigenvalues for A, I got 2 and 3.
Right. You see that real fast. The entry's on a diagonal. Do you know what an eigenvalue is, an eigenvector, Chris?
Do I know what an eigenvalue is and an eigenvector?
What's the definition?
Eigenvalues are oh gosh, what is it? The non-zero.
The eigenvalues is a scaling factor, which will scale a vector. And the vector is, when you operate on the matrix A, operates on X, it doesn't rotate it, it doesn't reflect it. It's just going to stay inert, but it might be scaled. And you must make sure that the vector is not 0.
Right.
This right here, I can use this idea to help me out. Look at this. If I take this previous equation, let's say if I was to pre-multiply by A, this gets me A squared. This gets me, factor out the lambda since it's a scaling, but AX, that's lambda x. So what does this tell you then about the eigenvectors or values as well for the square of the matrix? If lambda is in the spectrum of A, and so is the square and the square of the matrix.
Oh.
Now, from that insight, let's look at the equation in a little bit closer detail. Take your matrix equation and we're going to operate on X here. So whenever I operate on X, I'm going to get AX, or A squared X, and then the alpha is a constant, so I'm just going to factor it out. Then I'm going to have beta, and then the identity times X. Chris, that's X. So I'm going to incorporate that fact as well. And from up here, I know that AX equals lambda X, and down here, A squared X equals lambda squared X. Let's take it and replace it. Then let's factor out the X. And look what we got. First, we found eigenvalues by manufacturing it from another process, by using the definition. So I could go through the calculations and I could grind through it like such. Characteristic polynomial, manufacture like we have always have done, but it's too costly. What I want to do is stop what I'm doing, don't go through the hard way, and see if there might be an easier approach that I can manufacture what I need. Now, I know what the eigenvalues are, 3 and 2. Just take them and plug them in. So in one case, you're going to have 9 plus 3 alpha beta, 4 plus 2 alpha, and then beta. That's the spectrum for this matrix right here. Now that's pretty wild.
All righty.
It's kind of like computer programs. You can write a program with 1,000,000 lines of code, but if you can find how to do it in 10,000 lines, you can substantially speed up your program and give yourself the edge in the marketplace.
Dang. Okay.
Okay, well, let's look at your next one here. You had a question here on 4?
Yep.
Okay, so what did you try here on number 4?
Okay, so I was trying to figure out the so like we get to figure out our eigenvalues. And so to try to figure out our eigenvalues, I was trying to work through finding our determinants. Well, I was getting myself really confused on doing the determinants, and I could have been, just approaching our determinants wrong, but since we don't have a, what do you call it, an upper or a lower triangular matrix, 9K,
Okay.
yeah, okay.
So here's your determinant. So 7 times negative 5 minus negative 9 times k.
Right.
And how am I going to find eigenvalues? And they must be real.
Well, we got to find the roots.
And what's one way if I can find the roots if I can't factor?
It's a great question.
Quadratic formula.
Okay.
Now, once again, I'll take A as being 1. That's whatever's in front of the t squared. And the B is whatever is in front of the t.
Yep.
It is going to be negative b, but because it is a negative 2, I get 2. Plus or minus. And then negative 2 squared is 4. Subtract it off. 4 times your c value, your scaling constant in the back. And then times 1 all over 2 times 1. Now, in order for us to have real roots, it's all about the discriminant. the discriminant better be positive. Because if it's negative, you have the square root of a negative number, and that's going to be a complex value. So if you want to keep it real, make sure the discriminant is positive. Okay. Also, it can be 0, and you'll definitely make sure it's not negative that way. Now, if you want to make sure you have distinct roots, you need to make sure a discriminant does exist.
Right. So we need a real number.
So extrapolate your discriminant, pull that radicand out. And what you're going to do is bound it away. So you're going to bound it away and just make sure that that thing is never, ever, ever 0 or negative.
Okay.
The question now becomes, can you solve for k?
Well, we can. Just got to expand out that equation.
What I'll do is I'll take this piece that says a negative, I'll kick it to the other side, then I'll divide by 4. Then I'll add 35 to both sides.
So now we have 36, 9k.
And what I got to make sure when I divide by 9 again, it's not negative. I don't have to worry about flipping the sign. So as long as k is less than 4, Houston, we have liftoff. We are going to have guaranteed all the time distinct real eigenvalues. Okay, how about number 5? That's a great question.
Okay, so give me 1 second here. I'm just kind of looking at that problem still for just another second.
Sure thing.
So k would have to be less than 4. Okay. And so even though it's asking for 2 distinct, really, so you're saying that we could choose 1, we could choose 2. It doesn't matter as long as it's between 0 and 4, or equal to. Or, so will this be equal to or greater than 0 and less than 4, or does it have to be greater than 0?
As long as k is bounded above by 4, you are guaranteed to have 2 distinct roots. Now, this problem is not asking you to find the eigenvalues, just find the values for k, which will guarantee 2 distinct roots.
So even if you have, so you could then technically have a negative value in there.
You could.
Okay,
certainly.
Gotcha. Okay.
And here's a real easy one. Suppose k was equal to 0, Chris. What kind of matrix would you have?
You would have a lower triangular.
What are your eigenvalues?
7 and -5.
And 0 is less than 4, isn't it? Those are distinct because 7 is equal to -5. So if they actually wanted me to figure out the eigenvalues, then I can say, okay, I'll just pick k equals 0, and there it is.
Okay. Okay. Now it's making sense. Because eigenvalue, I was thinking for some reason I was mistaking k for like some eigenvalue, and now it's making sense. So, okay.
All right. How about number 5?
5. Okay. Let's see. 3, 4, and 5. Okay, so we want a 2 by 2 matrix with a trace of 5 and a determinant of -14. So yeah.
Remember that handy dandy identity again.
Trace of A is the sum of the diagonal. So trace. So we have t squared minus. Well, in this case, since trace is 5, would this be a +5 or a -5 here?
It would still be a -5.
Still a -5. Okay. So we have 5 t plus, and then we have a -14.
Good. So your quadratic is t squared 5t minus 5t minus 14.
Yep.
Now, my question is this. Can you factor it?
Should be able to.
Yeah, try
Okay.
factoring it.
So we have, because we have 1 and 14. We have 2 and 7. And that probably is already going to be our answer right there. Because if
Now,
we
it is
have,
negative, so you do have to worry about the negative cases.
yep. So yeah, because I look at which ones are going to give us a combination, and then I then go in forward and see, okay, which one.
I see.
So now for this one, wouldn't we want to have the 7 be a negative?
Chris, you got it.
Yep. So it'd be t plus 2t minus 7.
So what are your eigenvalues?
It'd be -2 and 7.
That's exactly right.
Okay, for some reason, I don't know why. Just as soon as we started doing this, it started making sense. I don't know why it wasn't making sense to me yesterday.
It's probably maybe a long day.
Could be, yes.
Okay, what number 8?
8. So there's 2 8s on here. The 8.
Oh, yeah.
So the second 8, the one on the right now, is their answer. I'm trying to figure out how, given the question, they got their answer. Because given A, find the matrix B such that B squared equals A. Well, I'm thinking, okay, we're just going to square A, so B squared, I realize I think B squared equals A, so we'd have to take the square root. Okay, I kind of think I'm seeing it already.
Okay.
Why I was screwing up and why their answer is correct. I'm still a little confused as to the X's.
Those are going to be your eigenvectors for the matrix.
Okay. Gotcha. Okay. Because I went about this with my head completely thinking something different, and I'm looking at it now. I'm like, oh, I know it. I now understand. Okay. Because we want to square our B to get A. We're not squaring A to get B. And yeah, my head was completely up and somewhere else. So
I got you. All right. How you feeling about it?
feeling okay. Yeah. So really, to do the square root, really, we're not doing anything crazy. We're just taking our D value and we're doing the square root, so that when you square it, it'll come up with the same value A.
Right. They're kind of using the idea. This idea of diagonalization of powering up that we were talking about the other day.
Yeah.
And they're going to say something like 1/2, 1/2 in order to get back to A. Because a half plus a half, using properties of exponents, will get you back to 1.
Okay. Gotcha.
Good. Anything else on this?
Let's see. Give me one quick second just to make sure. And where's my cursor? There it is. There we are. Let's see. Yeah, you know what? I got one more question, and it's something, I got through half of this question, but, we still wouldn't mind talking about it just a touch. So let me grab this question. There we are. There we go.
Oh, SVD.
Yep.
Have you had much chance looking into it yet?
I've gone through my lecture material, and I from a high level, it makes sense, and I'm able to see a lot of things, but I'm still kind of like, oh, okay, could use, because I know we're going to talk about that a little bit today, so maybe we can use this as a jumping off point for that. So,
Okay. What do you know about the SVD?
singular value decomposition. I do not know much other than so when we're so this equation we have three, at least in all the questions that I've seen thus far, we're given three components of our SVD. This is question 13. Where's my question 13?
Now, there are a few terms up here, like such as rank. Remember what rank
Mhm.
refers to?
Rank refers, so
The
rank is
number.
referring to the non-zero components of our, well, basically it's referring to these values here. So for this one, we have a rank of 3.
Okay, they're definitely related. Rank refers to things like the number of basic variables, the dimension of your column space for your matrix,
Mm-hmm.
and then I guess R is referring to the range in this notation.
I think, because let's see. Oh,
Or is
here's
it
my
referring to the row
questions.
space or?
Well, I think I'm trying to remember exactly. Let me get back to my notes here because
Okay.
I saw it in the notes. Okay, so the outer product expansion of the matrix rank 1, since R of A or RA is equal to the span of X, and RA transpose is equal to the span of Y.
Okay. Okay. Well, let's take a little closer look at the SVD. And I'll give you a nice quick introduction here to it. And
Because
this
yeah,
might actually
SVD,
answer a lot of your questions.
yeah, because I know this is U. This is I keep forgetting what that symbol's called, and then V
Sigma.
transpose, sigma, V transpose.
All right, give me one moment here, Chris.
Yeah.
Computers always like not to work when you want them to.
Ain't that the truth?
There's a little bit of an issue here. Let me see if I get this fixed. Okay, I think I got it fixed. All right, can you see the screen okay?
Oh, I can see. Oh, okay. We're switching screens here. Let me move you over to my big screen. Boom. All righty. I got you.
All right, so we got our singular value decomposition. Okay, so to start off, for singular value decomposition, it's kind of looking at an application. What's the cost of actually compressing data? Now, it's something that's a big interest to things like Netflix and Hulu and maybe YouTube, all the different platforms where they want to compress the data because if they sent you all the data, it'd be overwhelming and your system might actually crash because you can't handle it all. So that's a kind of an area of research. What's actually happening with compression? And we use compression for lots of other things besides with video. We can do compressions with graphics. We can do compressions like with a zip file. You want to transmit the data. And also you might want to unzip it later on, make sure you have all the information. So let's take for a moment just a typical screen, something like a 19 by 20 by 1080 pixel screen. Now, a pixel, you can think of it as being like a square dot, and it's just an individual entry. What I like to do is when you zoom in real close, it reminds me of a matrix. It's like you're looking at a matrix, looking at a monitor. But if you were to take this and multiply it out, 1920 by 1080, it's going to have roughly about 2 million pixels per frame. Now, it doesn't really seem like a lot until you realize for each second that's involved in a video, it's roughly about 29 frames just for 1 second. Now, to help us out, here's our good old friend Mario. And if you zoom in real close, you can start seeing all these different pixels, all these different square dots, and how they're just forming a nice little picture. Here they are. Now, for each one of these pixels, this 8-bit system, I have to color it in a certain way. Now, I got my red, I got my black, got my brown colors. And for each one of these colors, I also have to encode that information. Maybe in terms of like the RG green, like the red, the green, the blue spectrum, I can use that coordinate, the coloring scheme. I can also do it in cyans, maybe do something like with vectors, which are 4 dimensions. And this kind of just iterates again. If I look at my vectors, look how many components I have. I have 3 components. So just looking at colors, that's looking at a 3rd-dimensional object. Something that we kind of talked about earlier when looking at the color wheel, looking at a basis set. Because all I really need are my primary colors, my 3 basis vectors, my blue, my green, and my red. Okay, now here I have so much of the red I might want to take, like maybe 0.6 of it, and then maybe so much of the green, then so much of the red, kind of mix them all together to form the color I need. And in this kind of setup, you can kind of see the shape of Mario still. Okay, so that's the idea. When I look at all my colors, there's actually vectors behind the colors. But don't tell someone in the art department. I'm not sure if they'll like that too well, because what we're doing is we're painting by numbers in a sense. So I can decompose it in terms of the red spectrum, the blue spectrum, and then the green spectrum. I merge the 2 or all 3 of these together, and that's how I form Color Mario. So a resolution of 1920 by 1080 pixels again is roughly about 2 million pixels, where you have your width and you got your height. Okay, and that's what we're talking about. So how much data does a video use? Well, for my pixels, roughly about 2 million pixels per frame, and it's going to be about 3 bytes per pixel, one of those square dots in order to have the color. And there's 30 frames roughly per second. We'll kind of round it up. Makes calculations a little easier as opposed to using 29. But that's going to give us roughly about 187 megapixels, not per hour, but per second.
Dang.
And if I was to say, well, how much is it going to be for maybe even in a minute or a 20-minute episode just on Netflix, just a small little episode? Well, notice 187 megapixels per second, 60 seconds per minute. There's 20 minutes. Altogether, 224.4 gigabytes of data. If you think matters worse, let's actually go to a full-length picture, maybe 2-hour movie. Once again, we have 187 megapixels per second, 60 seconds per minute, 120 minutes in 2 hours. You ready? 1.3, not gigabytes, but terabytes of information.
That would be my monthly allotment of internet for 1 2-hour movie.
Something like that. So you can definitely see it's not sustainable. And let's put it in more practical terms. Let's say if you're going to watch it on your cell phone. Well, you can get some kind of data plan. But most data plans aren't going to have 1.3 terabytes of um, data available. So let's just say it's an average data plan is 10 gigabytes per month, and you're charged $15 for each gigabyte you go over. So for a 2-hour movie, you're definitely going over because, again, that's 1.3 terabytes. It's going to cost you about $20,000 just to take in, watch it on your cell phone here. That's not sustainable. Only the top tier of society would be able to watch movies, and your business model will quickly crumble. So what we got to do is find some way to compress the data so that it's more sustainable. So this is one thing. Look at Netflix. It's one thing that they look at, as well as Hulu and other things, YouTube, how I can compress data without losing information, at least not a lot of information, so it's still recoverable and you can still understand it. Basically, game over by Mario. Okay, so you have two different types of data compression. You got your lossly and your lossless. You have data compression in which you can lose information, so you cannot recover it once it's gone. And you have data which does compress, and there is a way to reconstruct every single bit of the details. You have JPEGs, and if you were to take a picture, maybe in Paintbrush or Photoshop, and save as a JPEG, and then zoom in real close, you will start seeing it's a bit fuzzy on the edges. You're losing information. MPEGs, you also lose some information. Now, I guess most of us aren't going to really notice that too well. All the difference in the sounds. If you're a musician, you probably would. MP3s and PNGs, these are going to be able to reconstruct perfectly. And for a long time, this is kind of the standard you would use, doing some stuff on the internet, posting pictures. But you also have other things like SVGs. We look at your vector graphics, which allows you to zoom in real close and zoom out real far without losing information. DivX and WMAs, just to list a few examples. Now, your SVD, the singular value decomposition, that's going to be the loss. You're going to lose information here. Hopefully, it's not enough information that's going to make much of a difference. Now, just a quick history of it. It kind of dates back to the 1800s, like a lot of things in mathematics, where a lot of mathematicians actually figured the things out, and it took the engineers 100 years, 200 years to kind of actually put some practical use to the math. The engineers make all the money. Mathematicians, they're like starving artists. Never make any money off of it. But it was kind of had a bunch of people who would contribute to the work over the years, and one of the most prominent ones was this guy named Jordan. You hear a lot about him in mathematics, as well as Sylvester. He also has a lot of things in the algebras. Okay, so they kind of discover all these things, all right, and there's Schmidt from the Graham-Schmidt process. That's exactly right. A real interesting history about with him too, But anyways, we'll kind of forget that here for the moment. But here in the nutshell, here's your SVD. Here's your structure behind it. Look at the geometry of the shapes. You got your matrix, and using the protocols of matrix multiplication, we'll have our square matrix U, and we have our sigma. That's going to correspond to all of our singular values, and we have our V transpose here in the back. We multiply them a certain way, we can reconstruct our matrix A. And your SVD is a way to factor your matrix, just like the LU factorization was, and the QR factorization. This gets you another way of how to do it, and it also gives you some extra information in the mix. All right, here are your steps of how to go about this, Chris. Something you might want to write down if you don't already have this. In order to form your V transpose, what we're going to do is calculate A transpose A. Now, the reason why we're looking at A transpose A is it's going to give us a symmetric matrix, and I can calculate the eigenvalues, guaranteed. If A is not a square matrix, you can't calculate its eigenvalues. So A transpose A, calculate a spectrum. After I calculated the spectrum, I do want to figure out the eigenvectors associated with it, and then we'll take the transpose. Okay. Now, let me know when you got this down. Move on to the next slide.
Well, you know what? I can take a screenshot really quickly, and then we can move on. So that way I can go back and write it down in after. All righty, I've got a screenshot.
Perfect. Okay. Now for the next one, you're going to form your sigma matrix. And this is going to refer to all your singular values. Now, something to take note of, we're using the eigenvalues of A transpose A, we're going to take the square root of them. And because we do have a real matrix, we're guaranteed to have real values when we go about this process. And our singular values are typically denoted with the sigma sub I.
So then so all the eigenvalues will be just the square root. We'll take the square root of that eigenvalue, and then that will be the basis for our sigma.
Those would be your singular values.
Singular values. Mm-hmm. And those would go on the diagonal. And then everything that's not on the diagonal would be a 0.
Right. Now, also, want you to kind of take a note here as well. This is going to get back to the rank question you had, but here we're going to have just k of them. I could load it up, go all the way down based upon the matrix. Block of zeros, and a block down here of zeros, possibly. Okay, just another shot of it. And then we're going to form U. So to form the columns of U, here's your algorithm. The ith columns can be 1 over the singular value. And we're going to take our eigenvectors, or excuse me, our eigenvalues, and we're just going to order them from greatest to least. So lambda I has the biggest magnitude. Lambda 2 has the next biggest magnitude. Lambda 3 has the following next biggest magnitude. So we're just going to order them from the largest to the least. So it's going to be in decreasing order.
Okay.
Now, here's an example just to better understand what's going on. And just to keep it simple, let's just use white pixels and black pixels. And if the bit's turned on, I'm going to label it 1. If the bit's turned off, I'm just going to label it 0. So in accordance to this diagram, I can get this matrix out of it. 1, 1, 0, 1, 1, 0.
And so we're saying white is turned on.
That's right.
Okay.
And when the bit's turned off, we'll just make it black.
Gotcha.
Okay, so A transpose A gives us our symmetric matrix. I then calculate its corresponding eigenvalues. Now, it is a 2 by 2, and we can use that nice little trick we keep talking about. The trace of the matrix, which is 4, and then we can take the determinant, which would be 3. We can then go ahead and factor in this one. Given us eigenvalues of 3 and 1. Now, after I have the eigenvalues, I then want to figure out the corresponding eigenvectors. Now, just going through the process, we'll have 1, 1, and 1, negative 1. And if I needed some additional eigenvectors, I don't really have enough. There's some other things I can do, or like a generalized eigenvector if I needed to. Okay, so here's your vector V, or your matrix V. And I do want to normalize. Remember how we normalize? We take the vector, divide it by the magnitude of the vector.
Yep, yeah, so, okay.
And then we'll take the transpose. So we got our eigenvector, normalize it, and then transpose it.
Okay, hold on. So really quick before we move on. So we're normalizing. Okay, so I'm looking at the normalization. So V equals V1, V2, and then we have everything on the left matrix there. Trying to figure out how so for normalizing, so we got to normalize and we're dividing it. How do we get root 2 on the top?
That's a simplification. You divide it by square root 2. It's just rationalizing it. So 1 over root 2, multiply numerator denominator by root 2. So just make sure you don't have a root 2 in your denominator. You don't have to. It's just customary to rationalize.
So technically though, that would be 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2.
That's exactly right.
Okay, gotcha. Okay, because that's what I was thinking. That's what like, okay, this will be this, and then my head, and then I saw that. I'm like, wait a minute. Okay, that makes sense then. Cool.
Now, in this case, it's a little hard to see, but we do have the matrix is rotated, but is symmetric. So it looks exactly the same.
Yeah, because symmetric. Yeah, because there's some. Okay.
Okay. Now let's form sigma. Remember, eigenvalues for 3 and 1. So these singular values, you take the square root of your eigenvalues. So you have root 3, and the square root of 1 is 1. Form your sigma matrix. And note that this may not be a square matrix.
Okay.
Now compute U.
And the reason we had 3 rows is because our original or alpha matrix had 3 rows. It was a 3 by 2 matrix, correct?
That's correct.
Okay. And you will always ensure that your singular value matrix, the sigma matrix, will have just as many rows as the alpha matrix.
That's correct.
Okay, cool.
Okay, so U1 and U2, just go into the algorithm, 1 over the singular value, and A times V1, or V1 again corresponds to the eigenvector, not for A, but for A transpose A.
So
just go back real fast so you can see that.
A transpose A. Gotcha.
Okay, that's what we're looking at.
So that's the new A that is being referred to for when you're computing U.
Okay.
Okay.
So when we go about the calculation for U1, singular values, and I'll go ahead and rationalize it so the square root's in the numerator. Matrix A, and then times the vector V1. Go through the calculations, and you found your U1 vector. Likewise, for U2, we'll go through the whole entire process, 1 over the singular value. Now, in this case, sigma 2 is going to be 1. Take matrix A and the corresponding eigenvector for A squared A.
Okay. So no, we're actually using the actual A on here. I thought, okay. Oh, I must have misunderstood you then when you were talking about A is the A transpose A.
I was back here. You're looking at the eigenvalues and eigenvectors for A transpose A, not A.
Oh, V is the A transpose A. Okay. That's where I got misunderstood. Okay, we're good then.
And make sure you do normalize. So you're going to update V1 and V2 to the normalized form.
Gotcha. Normalized.
All right. Now, if I need to find a third one, I can go ahead and do some like generalized eigenvectors. I can also look at a basis set and need something that's orthogonal. So I use the Gram-Schmidt process. Okay, so the final third one, we'll just go ahead and go about the whole entire process, orthogonalize it in regards to U1 and U2. And without going through all the nitty-gritty details we talked about in a previous session, this vector right here will pop out.
Okay.
Okay, now, next thing is put it all together. And there is your SVD. Singular value decomposition. Singular values, those are what's inside your sigma.
Dang. Okay. So then now so we got a 3x3 as our U, and that's because we had to figure out what our final, you were talking about finding that last column. Okay. Gotcha. Okay.
Now, let's go back a little bit. We talked a little about the SVD,
Mm-hmm.
and I kind of make mention of those blocks again, those block zeros.
Mm-hmm.
Now, if those are a bunch of zeros in my matrix, and I know they're zeros, when I go through the calculations, it's not really going to contribute much to the whole entire grand scheme of things. So what I can do is I can ignore those zeros when I start doing my block matrix multiplication and addition, whatever I got to do. So I went ahead and just kind of partition it off. It's not an augmented system, but just kind of partition it in terms of the blocks so you can kind of see it. Here's a K block of U's. Here's your K by K submatrix and a K block of row vectors. So we're going to look at what's called the reduced singular value. And here's the idea. When I look at all my eigenvalues, if my eigenvalues are small enough, let's say if I have an eigenvalue which is 5 and an eigenvalue that's 0.00000007. Well, how's that small eigenvalue going to contribute to the larger eigenvalue? It doesn't. It's pretty much insignificant for the most part. And if you start powering it up, it becomes less and less significant. It's not going to contribute much to the system. So I can take those small eigenvalues and I can just truncate them and push them off and don't worry about it, just worry about the bigger ones. And that's where you get that lossy compression, where you're removing information, but it's too costly to transmit everything. So I just transmit the relevant information. The smaller details are not going to contribute much to the overall grand scheme of things. And that's the idea. So I can look at my reduced SVD. I can just look at the block on top, and this gives me a better compression in a sense. So I'm using less information, where I'm looking at a M by K, and so I'm just looking at entries on the diagonal. Everything else is going to be zeros. There's only K entries here, and I need to actually record in memory or storage. And over here, I have my vectors, and I have K of them, but they are going to be linked in. So I have to have N, so Kn entries all together. So in the very end, real fast, I guess, the rank R approximation, we order our singular values, and we just truncate the ones that we don't really need, or the ones we think is not being too relevant to the problem.
Okay.
So I might get rid of these back here. So an example of a rank 100 approximation, and just keep it simple again, calculation purposes, we'll say an HD 1000 by 2000 screen, so roughly about 2 million pixels again. Here, when I have my size, I have my RM, and then RN, and then R. That refers again back to looking at this size here.
Mm-hmm.
Here's my U. Here's my sigma. and here's like my V transpose. Instead of using 2 million pixels information, I can look at 300,000, roughly.
Dang.
And if I looked at the ratio, I see that this is going to get me a savings of quite a bit, about 85% compression. That's a lot. Remember our problem at the very beginning? About roughly 1 terabyte of information.
Mm-hmm.
Let's see how that compares now. So with uncompressed data, just doing pixels and frames, it's going to be about 1.3 terabytes of information. But if you use our rank 100 approximation using the SVD, we can save a whole bunch of information, roughly about 1.1 terabytes. Now, instead of using 1.3 terabytes, we now have a movie down to 200 gigabytes. Now, it's still a lot,
Mm-hmm.
but it's a whole lot less than what we started off with. So that's what's going on with the SVD. I can use it in this regards to do data compression, stuff with Netflix, and whatnot.
Okay. Okay, because so now I have a question here. So because we did a lab where we worked with singular value decomposition, we took an image and we worked on the compression. And one of the questions was referring to, okay, at what rank would we actually be sending more data than the original image? And because we were dealing with an image that was, I believe it was like 249 pixels in height and 375 pixels wide. And they were like, okay, what rank would, we be sending more data? And so is there, and for me, I thought that was kind of weird that when looking at this, that we would be able to send more data than the original image. And is that something that can actually happen, or is this something that they just kind of pulled out of their hats for the purpose of this for this lab? Is that something that can actually happen?
Oh yeah, oh yeah.
Okay.
If I know I have a bunch of zeros in my matrix
Mm-hmm.
and I send the information anyways, why would I do that? I can use something called a sparse matrix, where I just send the locations where it's not zero and give you what those entries are, as opposed to giving all the information. If you have an n by n matrix, that's going to record n squared entries. And if I'm just looking, let's say at just a 10 by 10, that's going to be 100 values right there I would have to transmit. Or if I know it's going to be a diagonal matrix, I'll just send you the entries along the diagonal. At most, that's going to be 10. So I can send you less information and you can still recover the picture you need.
Gotcha. Okay.
Yeah, so things like that can definitely occur. And those kind of situations, you have to kind of look a little closer to see what's happening. But if you're sending a signal out of space, you probably want to make sure you get a good burst of information before it goes to the dark side of the moon.
Gotcha. Okay.
Because then, how can you transmit the information?
Gotcha.
Good. Well, how do you feel about the SVD now, Chris?
Feeling better. I'd love to go through that last problem though, just to make sure that everything is, everything is working the way it's supposed to. So it's not asking us to create the SVD, because I guess the SVD, and a lot of the questions that they've asked us in homework and everything, they've never really asked us to go through. I mean, they've asked us to find, okay, like create the U or something. They haven't asked us to create a full singular value decomposition in any of our questions. It's mainly been, hey, here's your SVD, here's a bunch of questions on it. So
and the rank that would refer to the number of singular values that we showed, like in the reduced singular value decomposition. So if I was going to write out my partitioned matrix, I might look at it like this. or have that 3x3 block. And I have my 3 non-zero entries.
Okay.
Find the rank 1 matrix B. What is matrix B here in this case?
Matrix B?
I guess what they're referring to here is if you were to zero these entries out, see how this is 100, these are 10, that's not going to contribute much. And this would be a rank 1 matrix now, because everything else is zeros. There's only one non-zero entry. If you were to calculate this, I believe that's what they want you to do for matrix B.
Okay.
Then they just want you in part E, calculate using the Frobenius norm.
Okay, so because in the rank 1 matrix, so in their little note thing they gave us, so that was D, yeah.
And then for F and G, now you're using a rank 2 matrix. Do the approximation.
Find the rank 1 matrix B that is the closest matrix.
Go ahead.
I was just saying that so the rank 1 matrix B is the closest matrix of rank 1 to A is given by, and then and I apologize. I think I'm losing my head here.
Oh, no, that's fine. Take your matrix up here and zero out these entries right here.
Oh.
Now it's a rank 1. Likewise, if you want to get to rank 2, take your SVD and zero out this entry here. So then you would have your rank 2 approximation. Put it over here to the side. And they want you to call this one matrix B. And this one they want you to call matrix C. Then they want you to use the Frobenius norm to go about the calculations, to get the metric on the matrix. Okay. Does that make sense how you can go about the approximation rank 1 and rank 2?
Okay, I think so, because I guess I was getting hung up because in the notes they were talking about, let's see, being rank 1. Let's see, I'm trying to find where it said that. Rank, so the outer product expansion is a matrix of rank 1, but okay, I guess I was misinterpreting what they meant by rank 1. I thought rank 1 was some sort of title or just a general definition, whereas they're referring to rank 1 being a singular value in the matrix, a singular non-zero value. Okay, I think I see that then, yeah.
And this is how you can do the Frobenius norm. It's going to be the square root of it's different from the Euclidean norm that we were working with, but you have the square root of the trace, and then you can say M times M transpose. You can also do the M transpose M if you wanted to, or they're going to be equivalent here.
Okay.
And they want you to calculate the difference. So once you get your matrix B, matrix C, do you calculate B minus A? Now, you can also set this up in terms of B minus A minus B or B minus A. When you do the metric, it doesn't really matter in N, so you don't have to worry about it. Just make a choice, really, Chris, and just go with however you want to set up the M matrix.
Okay.
and then run through the Frobenius norm. So it's going to be computational here for you going with these problems.
Gotcha. Okay.
Okay. Any questions on that?
No, I no, it's making sense, and that was the presentation was very helpful. So
Good. I'm glad you enjoyed that. All right. So your exam, is that tomorrow?
tomorrow, yep, technically it opens up tonight at midnight, and then I have until midnight 11:59 tomorrow evening to take it. So yeah.
Okay. So you feeling ready for it?
I mean, as ready as I can be. I'm trying to, rework through a lot of information. I'm feeling, a lot better about this most recent material, but I'm going to spend a little time this afternoon going back over some of our previous material and just trying to make sure that I'm kind of remembering how to do, especially stuff that we did like week 1, week 2.
Mm-hmm.
Because there's a lot of, we're going to be covering, everything. So, but again, just got to make sure I just get those 8 points and then I pass. So
Yeah, that's right. That's all you need.
Yep.
Now, your exam, you got to turn in by midnight tomorrow night?
Yep, and it's a 2-hour exam,
Okay.
where we're given 2 hours. And what's nice is we're allowed 2 submissions, and we're allowed to submit it once. It'll grade it. It'll tell us, hey, you got question 1, 2, 10 wrong. And depending on how the question's set up, it might even tell us, okay, you got this specific portion of the question wrong. So
Okay.
that's helpful. So
Well, as you're studying later on tonight, getting ready for it, if you feel like you need a little bit more help, just let me know and we can jump into another session, help you get ready for it. I have a few openings tomorrow. We can definitely do that if you need to do this. So
cool. Well, I will let you know if I need any additional assistance.
Help getting those extra 8 points. I got you.
Yep.
Well, Chris, I've been having a great time helping you these past few weeks with the linear algebra, and it's been kind of an accelerated course here for you. But you've been doing a great job keeping up with the material. This stuff is nothing to sneeze at. It can definitely be a bit complicated, as you have seen, but you're doing a great job keeping up with it.
Thank you.
Highly commendable. And if you need any help in the future, just let me know. I'll be glad to help you any way that I can.
Awesome. I appreciate it so much. Thank you for being available and being able to help me out. I don't think I'd be in such a great position that I am right now without your tutelage, and so I tremendously appreciate it. Thank you.
Oh, you're more than welcome, Chris. And once again, if you need anything, just let me know. Keep in touch and let me know how the exam goes.
I absolutely will.
All right. You have a great day.
Thank you. Same to you.
All right. Bye.
Bye.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.